Hi, my name is Kenji Yasunaga. This talk is about a new framework of bit security. This is a joint work with Shun Watanabe. In this talk, we want to consider what is bit security. It is, in some sense, a well-established measure of quantifying the security level of cryptographic primitives. We say primitive P has k-bit security if every adversary needs 2 to the k operations to break P. So the question is, how can we define bit security? As an example, let's consider the case of 1N function. Let f be a function. We say an adversary A breaks 1 variance of f if, given a sample f of x, A outputs the string y satisfying f of x is equal to f of y. We want to consider the computational cost needed to break 1 variance. We have two simple solutions. The first one is the brute force search. For every string y, the algorithm checks if f of x is equal to f of y until it finds a solution. The second one is random guessing. For random string y, the algorithm checks if f of x is equal to f of y. The algorithm iterates the procedure until it finds a solution. In either case, the algorithm needs order of 2 to the n iterations to find a solution. So the total computational cost is order tf times 2 to the n, where tf is the cost for evaluating the function n. And we may have another solution. Namely, there is some good algorithm A with computational complexity T such that A breaks the 1 variance with probability epsilon. In this case, let's consider what if we invoke the algorithm in total n times. The probability that some algorithm breaks 1 variance will be amplified to epsilon n. Since it is sufficient to choose n is equal to 1 over epsilon, so the total computational cost of order n times t is equal to order t over epsilon. We have seen 3 solutions to estimate the cost of breaking 1 variance. We notice that the cost of order t over epsilon is consistent in all solutions. In the brute force search, the cost is tf times 2 to the n, and epsilon is equal to 1. When we use random guessing, cost is just tf, and the epsilon is equal to 2 to the minus n. So, based on this observation, the bit security should be defined as the minimum value of the log base 2 of t over epsilon. And this way of defining bit security can be extended to other search type primitives, such as signature schemes and message authorization codes, and also the search type assumptions, such as factoring, DL problem, and CDH assumption. So the question we want to ask in this work is how to define bit security of decision type primitives and assumptions, such as pseudo-random generators, action schemes, and DDT assumption. In decision game, the adversary's winning probability is designed to be close to 1/2. So we usually define the advantage of the adversary as 2 times the absolute value of the winning probability minus 1/2. So we want to know this advantage is the right measure for evaluating bit security. In this work, we introduced a new framework for defining bit security. It is defined for security gains. And we apply the same operational meaning for search and decision gains. The interpretation is that game G has k-bit security if every attacker needs computational cost up to this k for winning the game with high probability. Since we consider that two types of search and decision games should be structurally different, we define the winning condition for the two types differently. And as an answer to the second question in the previous slide, we show that in our framework, the learning advantage is the right measure for evaluating bit security of decision games. And we show several natural reduction of bit security between security gains. And finally, we compare our framework with the one proposed by Mitchell and Walter in 2018. Now we describe our framework. There are two adversaries, an inner adversary and an outer adversary. The inner adversary plays a user security game G, which is an interaction between an adversary and challenger. We assume that for every game, a challenger chooses a random secret U of length n. For such games, we usually require that the adversary's winning probability should be close to 0. For decision games, the secret is just a bit, and the winning condition is to predict the bit U. In this case, the winning probability is designed to be close to 1/2. And the task of the outer adversary is to invoke local game G many times to amplify the winning probability. Next, we will define the winning condition for the outer adversary. First, consider the case of the search game. The outer adversary collects information from the inner adversaries. Here, we assume that each inner adversary plays an independent game with fresh randomness UI. The winning condition of the outer adversary is that there is some inner adversary who wins the local game. So the task of the outer adversary is to invoke inner adversaries sufficiently many times so that some inner adversary wins the local game. Next, consider the case of the decision game. We assume that each inner adversary plays an independent game with consistent secret bit U. Namely, a secret bit U is initially sampled, and the same secret is used in each local game. After collecting information from the inner adversaries, the outer adversary finally outputs his prediction U prime. The winning condition is that the prediction is equal to U. So the task of the outer adversary is to invoke inner adversaries many times until he can collect sufficient information to predict U. In our framework, the bit security is defined as the minimum value of the log base 2 of n times t, where n is the number of invocations by the outer adversary, and t is the computational cost of conducting the local game. The minimum is taken over all inner and outer adversaries with the restriction that the outer adversary wins the game with probability at least 1 minus mu, where mu is some small constant called the error probability. This formulation means that the bit security is the log of the total computational cost needed to achieve the winning probability at least 1 minus mu. We have several implications. First, for such games, the bit security must take a finite value. The reason is that if the output length of the adversary is m, a random guessing adversary can win the game with probability at least 2 to the minus m. So the total cost of 2 to the m is sufficient to win the game with high probability. So the bit security is at most m. In contrast, addition game may have infinite bit security. We can understand it by considering the one-time path encryption or perfectly secure encryption schemes. Since no adversary can increase the advantage in this indistinguishability game, we cannot amplify the winning probability to 1 minus mu. So the bit security is infinite. Finally, we observe that in the addition game, the outer adversary collects samples from inner adversaries to distinguish the two cases. This is the task called binary hypothesis testing in information theory or statistics. So we can use the existing knowledge from the literature to characterize this task. We characterize our bit security in the following theorem. For any security game G, the bit security is equal to the minimum value of the log base 2 of T over the advantage of the inner adversary. Namely, we can exclude the outer adversary and the bit security can be evaluated by the inner adversary, where the advantage is defined as follows. For such games, it is equal to the winning probability of the adversary, which we can easily understand. For decision games, the advantage is called the Renyi advantage, which is equal to the Renyi divergence of order 1/2 between two distributions A0 and A1, where AU is the output distribution of the inner adversary under the condition that U was chosen as a secret. We investigate the behavior of the Renyi advantage by comparing it with the conventional advantage. Suppose that the winning probability of the inner adversary is equal to 1 plus epsilon over 2. Then the conventional advantage is equal to epsilon. The Renyi advantage is given as in the previous slide. And we show that for any decision game, the Renyi advantage is bounded below by epsilon squared and is bounded above by epsilon. Also, we show that the Renyi advantage is equal to the lower bound for balanced adversaries, where we say an adversary is balanced if it outputs any value with at least constant probability. Using this proposition, we can resolve a peculiar problem of linear tests for pseudorandom generators. Let's look at this problem. Consider a pseudorandom generator G with seed length n. It is known that for any pseudorandom generators, there exists a linear test T that achieves the conventional advantage of 2 to the minus n over 2. Since non-trivial linear tests output 0 and 1 with equal probability, they are balanced. Thus, the Renyi advantage will be 2 to the minus n from the previous proposition. So if the bit security is equal to log base 2 of T over the conventional advantage, the bit security must be at most n over 2. However, it is counterintuitive because it seems unnatural that n-bit stage pseudo-random generator must have bit security at most n over 2. In our framework, since the bit security is characterized by the learning advantage, it is possible to achieve n-bit security. And we note that the Mitchell and Walter also resolved this problem by their framework in a different way. And in our framework, we show several natural bit security reductions. K-bit secure pseudo-random generator implies a K-bit secure 1 function. And K-bit secure into CPA encryption schemes implies the K-bit secure 1 CPA encryption scheme. Also, the K-bit secure DDH assumption implies K-bit secure CDH assumption. And regarding the Gold-Rahil-Levin theorem, we show that K-bit secure 1 function implies a K-bit secure hardcore predicate for balanced adversaries. However, proving the general case remains open. For the distribution approximation problem, we show a natural composition of bit security. Suppose that game G employing distribution Q has K-bit security, and suppose that two distributions P and Q are K-bit secure in this interval. Then we show that game G employing distribution P instead of Q is K-bit secure. And this relation holds both in search and decision games. We briefly see the bit security framework proposed by Mitchell and Walter. They define the bit security as the log base 2 of T over some advantage introduced in their paper. It is defined using the mutual information and the Shannon entropy of random variables x and y, where x is the random secret of the game, as in our framework, and y is defined as false. It is equal to the failure symbol board if the adversary outputs board, and it is equal to x if the adversary wins the game. And in other cases, y is chosen uniformly at random under the condition that it is not equal to x. This advantage captures some correlations between x and y. However, it is difficult to understand what it means in this form. After introducing the advantage, they showed that that advantage can be approximated as false. For such games, as in our framework, it is the winning probability of the adversary. For decision games, it is equal to alpha A times the square of 2 beta A minus 1, where alpha A is the probability that A outputs the value other than board, and beta A is the conditional probability that A wins a game G under the condition that A outputs the value other than board. By this characterization, we can see that if the conventional advantage is in decision game is at the most 2 to the minus k over 2 for every adversary, then the game has K-bit security. Also, in their framework, the classical Gold-Levin theorem gives a tight reduction. Namely, K-bit secure 1 function implies K-bit secure hardcore predicate. Compared to their results, the difference from our framework are as follows. First, our notion has an operational meaning. Second, if the conventional advantage is at most 2 to the minus k over 2, then it does not imply that it has kept security. In our framework, the bit security lies between k/2 and k. Also, proving the tightness of the Goldilocks theorem. To prove it, we need to improve reduction algorithms. We conclude our talk. We introduced a security framework with operational meaning. The interpretation is that game G has kept security if every attacker needs a computational cost of 2 to the k or within the game with high probability. We show that in our framework, the linear advantage is the right measure for evaluating bit security. A possible future work is to give a tight reduction of the Goldilocks theorem. And since we have several frameworks to evaluate bit security, people may wonder which notion should be employed. So it may be beneficial to discuss the measure for selecting the bit security notion. For example, building some axioms for bit security may be possible. That's all. Thank you.